the organizers for setting up this very nice program and also conference here at KITP. It's a great pleasure to be able to close the conference today. So I'll try to keep it simple and easy and maybe also entertaining. Maybe you guys are going to let me know. But please, feel free to ask questions like as usual. If you can keep the question towards the end, that's okay. But if, it's absolutely necessary so that you understand what's going on, then just shout out loud. All right. So that's joint work together with Giovanni Chemin at PKS and Marcus Schmidt in Regensburg and Jülich. And the topic for today is learning to stabilize non-equilibrium phases of matter with active feedback and partial information. So the motivation for our work goes back to the year 1871, when Maxwell conceived of a being whose faculties are so sharpened that he can follow every molecule in its course. This would be a being who can play a game of skill with the molecules, as we do with larger bodies, such as billiard balls, that is to say, direct them and make them collide just as we please. And Maxwell pointed out that only we can't, we're not smart enough to create such a being. Now, this being was later dubbed by Lord Kelvin the sorting demon of Maxwell, and as you guys know, what it does is the following. So imagine you have a container of gas of molecules, some of them at some finite temperature, and some of them move a little bit faster, others move a little bit slower. And then what the demon does is it keeps track of the positions and momenta of all these particles in some record. And then every time that a hot particle happens to approach this bipartition here to the left, then the demon opens up a door and then the particle goes through, whereas all the slow particles, cannot move to the left. And vice versa, every time a cold particle from the left partition is approaching this opening here, then it can also be let through by the demon. And so, as it goes, this dynamics essentially cools down the system and therefore extracts entropy from the system. And so, Maxwell conceived this being as, an example of a violation of the second law of thermodynamics. And so it took actually almost 100 years, and in particular developments in information theory, when Claude Shannon basically taught us how to measure information in terms of entropy, for Landauer to actually realize that for the demon to be a finite being, and as such to have a finite memory, it's actually required that it has to erase some of the information about the positions and the momenta of these particles, and this erasure inevitably creates entropy. So, if you now fast forward to the year 2025, we find ourselves, in particular during this conference as well, thinking about quantum information. And as we know, quantum information is inextricably related to entanglement. And in particular, in the last maybe 5 to 8 years, advances in quantum simulators and quantum computers have shown that it is possible to now do projective measurements on these systems, like, these snapshots that Emmanuel was talking about yesterday, and then use this information in order to feed it forward into the system. In other words, in order to apply feedback control on that system. And so one example, or two examples that were mentioned, I think, in a couple of talks already, is that by doing this, one can essentially prepare long-range entangled states, such as the ground state of the toric coat or the GHZ state. And this is possible because this classical post-processing essentially allows us to circumvent the locality constraints that are native to unitarity. All right, so the question that I want to pose for today's talk is how can we utilize information for active feedback quantum control? And to answer this question, we're going to define a game of skill, not of molecules, but of qubits, a game that is known as unitary circuit game. And so it goes as follows. Suppose you're given a chain of n qubits, as I'm showing here. And what you can do is you can apply random Clifford, let's say, gates on neighboring qubits, so local gates. And as you do this, as you kind of know, you can measure, the total entanglement. This is the sum of the different entanglements across all these bonds. And as you track this quantity as a function of time, what you see is that eventually the system reaches a maximally mixed state, or so-called infinite temperature state. And one thing that you have to keep in mind about these Clifford circuits is that entanglement is created or destroyed at each bond in bits of log 2. And sometimes it can also stay the same. So one thing I want to emphasize is today there will be no measurements, so my circuits will be purely unitary. And so, okay, so this is just the setup now. The question is, what is the game, right? So suppose now that you have two competing agents, one orange and one blue, and the game proceeds as follows. So every step of the game, you toss a coin. And then with probability 1 minus p, the so-called entangler plays. So the entangler chooses a bond at random, and then it also samples a random Clifford gate from the Clifford group, and then it places it there. But with probability p, the disentangler gets to play, and the disentangler also places a gate on a random bond, but this time, now that it's selected the bond, it then basically loops through all, I think, roughly 13 or 14K 2-qubit Clifford gates, and then it picks one that will disentangle that specific bond, or that will reduce the entanglement by log 2 on that bond. And so as you can imagine, now these two agents are essentially competing, and the name of the game is, to prevent entanglement from building up, okay, starting from a product state. So this was introduced a couple of years ago in Frank Polman's group, and then what they did is they looked at the total entanglement entropy as a function of this probability to play the game, the so-called bias parameter. And in particular, there's some stochasticity in this game, as I just explained, so you can imagine that these quantities fluctuate, so one can also average over different number of realizations of this game. And so what you find is that if the parameter p is very large, that is to say, if the disentangler gets to play sufficiently often, then the state that you find is essentially an area law state, whereas if the probability is not that large, then you find a volume law state, and in between there seems to be a phase transition. The different curves correspond to different system sizes, and this is, like I said, a phase transition between the area and the volume law. Okay, so this is all very nice, and so what we want to do now is we want to ask whether we can change the properties of this steady state here using active feedback control, using essentially a kind of a Maxwell demon. And the short answer is yes, we can do this. In particular, we're going to show that active unitary, purely unitary feedback control can break detailed balance here in this steady state, and therefore sustain non-equilibrium states. And in particular, if you have sufficient amount of information, then the informed strategies can actually fully suppress or fully eliminate the volume law phase. Moreover, one tool that we will introduce to do this is reinforcement learning, and I will hopefully convince you that it is a very natural tool both for feedback control and also to quantify the amount of information that is needed to do this. And last but not least, we'll also look at how much information is actually necessary, and what we'll show is that there is a critical threshold to stabilize area law steady states. All right. So this is the outline for today's talk, right? So we'll talk about equilibrium and non-equilibrium phases. Then we'll, introduce this random and so-called greedy agents, and then we'll talk about partial information and reinforcement learning. Okay. So let's take a look at the nature of this steady state here. So once again, what we're doing is we're playing this game where there's a disentangler and an entangler, and then there's some stochastic dynamics, and they're competing. Essentially, one of them wants to increase the entanglement of the steady state, the other one wants to decrease it. And so you go into the steady state, and then the interesting point is that you can view this as a Markov chain dynamics over the set of stabilizer states, which is essentially a discrete set. And once you have that, you can ask the question, well, does the steady state distribution of this Markov chain obey detailed balance, in which case you would have an equilibrium steady state, or does it not obey detailed balance? So let's see how that works for this random strategy that we just introduced. So let me just remind you, the random strategy goes as follows. You pick a bond at random, and then you apply a Clifford gate that reduces entanglement across that bond, okay? And notice that in order to find the gate that actually reduces the entanglement, you need some information about at least the local density matrix on that bond, right? And so, there's information that's required. Now, Shannon tells us that whenever there's information involved, then there's also entropy, right? And we know from statistical mechanics that if you produce entropy, then this drives a system or a state out of equilibrium. And so what this means is at least it gives us like an intuitive way to think or to understand why feedback control, whenever it contains sufficient amount of information, actually can break detailed balance, even though the dynamics is purely unitary, okay? Now, let's see, how we can think about this phase transition from this perspective. Now, in this language, what we see is that this transition now becomes a transition between a non-equilibrium area law state at large values of P and an equilibrium, that is to say, infinite temperature volume law state at probabilities below the critical point. So, those of you who are thinking about like quantum dynamics, this is something somewhat related or somewhat similar to the thermal versus localized transition in MBL, although the physics is arguably sufficiently different. Okay, but what happens from the perspective of information, right? So the idea is that there's a critical information density as you scale the system up into the thermodynamic limit, and this information density vanishes below the critical point. In other words, the disentangler doesn't play often enough. There's not enough information that goes into our daemon, right? Whereas on the other hand, for probabilities greater than PC, there's a finite critical information density, and therefore the state is an area law state. Okay. So this was, the random agent. And the question is, once again, can we change the critical properties now of this steady state here if we use this information? First of all, if we use more information, and then if we use the information in a wise way. So let's define the next best thing, right? So you can say, okay, this is a random strategy. So the disentangling agent was picking those bonds here to place the disentangling Clifford gate randomly, uniformly at random. So maybe there is something that's a little bit better that we can do. So let me introduce the so-called greedy strategy. So this is a deterministic strategy which proceeds as follows. So first, what we do, or what the agent does, is it computes the entanglement across each of those bonds, neighboring bonds, and then it identifies those bonds where the Clifford gates actually can reduce the entanglement, right? So not every bond, allows to reduce the entanglement, but some of them actually do. Why? Because entanglement can only go up or down by essentially a unit of log 2 or stay the same, right? So there's like an intrinsic constraint that comes from the dynamics. But once we've identified the bond where we can reduce the entanglement, then, maybe there are many of those, maybe there's just one. What we have to do is we have to pick, one of those, and then we place the disentangling gate there. And notice now that the process of identifying bonds where Clifford gates can be applied, we want to, check this over all possible bonds, now requires a global amount of information about the system, okay? It requires me to check all these bonds. And if I now look into what happens out of the transition, what we see is a completely different behavior in some sense. So first of all, this is the total entanglement as a function of the bias parameter. We see here, the previous transition point for the random strategy. And what we see now is that this transition point shifts to the left. So this is now, there seems to be, a bunch of curves that in the thermodynamic limit would converge to another critical probability, the one for the greedy strategy. And in particular, you see that entanglement, or the total entanglement, vanishes continuously, unlike the previous transition, which was discontinuous. And once again, from the perspective of information theory, what we find is that the transition between, that we now have a transition between two non-equilibrium phases, right, steady states. There's the area law state, which is basically the same as before, where the disentangler doesn't play often enough. But now the volume law state is also non-equilibrium, because as you can see, entanglement can take any value in the thermodynamic limit here, right? And that's something that you cannot have, usually in these unitary circuits, simply because, we typically say that unitary dynamics can possibly have only one thermal state, and that's the infinite temperature state. The reason, you can find such a scenario occurring here is because you have this external feedback control that actually, messes up the information entropy balance and therefore brings the system out of equilibrium. Okay. So this is, the greedy strategy. So far, so good. We have, a phase transition between two non-equilibrium states. So let's actually take a look at the steady state distribution of entanglement for a few different values of these bias parameters here in the stationary state. So I'm showing you here on the y-axis the entanglement distribution as, a function of all the bonds, right? For three different values of, this gain probability. And the first thing that you see here is this, light gray pyramid here. This is the so-called Page curve. Okay, so that's the maximally mixed state. It's essentially, what comes out of the Page curve, in this Clifford circuit. And what you can see here is that, if the disentangler seems to play often enough, and often enough is really not that frequent, it's basically 15% of the cases, then, entanglement is relatively low. So in this picture here, I forgot to say, the total entanglement is actually the area that you see in the gray shaded squares. Okay, and as you can see, you decrease the value of this gain parameter and this bias parameter, and therefore the entanglement of the steady state becomes higher and higher. And you can see in these figures more or less how this entanglement is distributed. And if you're wondering, why entanglement is distributed, in this asymmetric way here, this is because, whenever we said that whenever we have, more gates or more bonds where we can place a disentangling gate, then we have to, break that symmetry. And the way we do this is by choosing the leftmost. So that's basically a choice that I have made. Okay. So far, we've seen the random strategy, we've seen a greedy strategy. This is kind of, the simple thing one can do. But is this really the optimal way or the most efficient way to inhibit entanglement growth with the amount of information that we're using here? Can there be better ways of doing this? And the answer is yes, there are. So let's ask the question, why could actually there be better strategies here? So how could a strategy be better than what we've just defined in terms of checking all the bonds and then just placing the gate greedily? Well, if you think about it for a second, then you'll realize that, this is a game, and as we know usually from playing all kind of board games, sometimes you can do better if you try to plan ahead. So you can imagine something like a plan, something like an agent that plans which bonds to place the disentangling gates on. So far, both the entangler and the disentangler were placing, the gates on a random bond. Now, I'll keep the entangler to place, the gates randomly because this is just creating entropy in my system. But I want to ask myself the question, can the disentangler now find a better strategy, one that uses planning, to place the disentangling gates? And what this will do, or what planning actually does for you, in some senses, it turns, the local in time optimization into a time non-local optimization. And, the analogy here is if you think about playing a board game, let's say chess or so, you can sacrifice, a piece in order to win the game in the longer run, right? So that's, a move that is obviously, non-greedy at every time step of the game, but then it might become beneficial in the longer run. So this is an example of these time non-local optimizations. And so the question is, if we have a tool that does such a non-local in time optimization, can we do better? The only problem is it's very difficult to model this, right? So if you try to model, all the moves and come up with a deterministic strategy, because the circuit dynamics is inherently stochastic, right? So in some sense, we're not smart enough to write down such a strategy that works right away. And this is where reinforcement learning actually comes to the rescue. So what this does, so first of all, reinforcement learning is a variant of machine learning for those of you who don't know, but for the purpose of this talk, this is just going to be a black box. And what it allows us to do is it allows us to minimize the long time total entanglement in expectation. So not just, over single trajectories, but over multiple realizations of the game. And, another reason why we're using this tool is because this has already been proven sufficient for finding interesting strategies in game setups. All right, so here's how reinforcement learning works in a nutshell. So the reinforcement learning algorithm is essentially a black box. What this black box is doing is similar to the daemon of Maxwell. It's, keeping track of the state of the system in this case. Because this is a Clifford circuit, I can represent the state in the form of a Clifford tableau. And so this Clifford tableau goes inside this black box, and what comes out is a probability distribution over all the different bonds. So basically, with using this distribution, my agent can decide, how likely is it to place my disentangling gate on this bond, or on this bond, or maybe on that bond, okay? And so, in that sense, this black box is nothing but a variational approximation for this strategy. And the reason, or another reason that I'll show towards the final slides of the talk, why reinforcement learning is actually useful is because it allows us to process information in such a way that we can dial the amount of information that goes into it. So, a natural question to ask here is, okay, maybe I cannot know everything about my system, right? What happens then, right? So this is something that's coming up next. But this is naturally, can be framed naturally within this framework. Okay, so once again, here's the feedback optimization loop. So what you do is you throw the dice to play the game. Then, if it's your turn, you observe the state of the game. This goes into the black box. Out comes the distribution. According to this distribution, I, choose a bond. And then, once again, once I've chosen the bond, then I loop over all possible Clifford gates deterministically to find the one or a one that disentangles, that lowers the entanglement, better said. And then the whole thing repeats over and over again. And what you end up having in the end is the following procedure. So you play the game by generating a bunch of circuit realizations using the current strategy pi. And then, in order to improve the strategy, you do this by minimizing the total expected entanglement. Okay? So I'm not, again, giving you the details of precisely what's going on in the algorithm, and I'd be very happy to tell you more about this afterwards. But this is more than what you need in order to follow the next slides. Okay, so now let's see how this agent actually learns. What I'm going to play for you now is a learning movie. So here, there's two plots on that slide. So on the left, you're going to see the figure of merit. So you can think of this quantity as being proportional to the negative average entanglement over trajectories. What you should know is that lower values mean bad performance and higher values mean good performance. The more interesting plot is here on the right, where you see the entanglement distribution as a function of, the bonds, or I call them locations here. And this is done now for a fixed realization. And what you see here, or we'll see here in the top right corner, is actually instantaneously what happens within, a given trajectory with the entanglement, with the total entanglement as a function of the circuit time. So as you can see, in the very beginning of training, so after maybe something like a couple of hundreds of training iterations, the agent is fairly dumb. There's a very dark colored red, rectangle here, which is sort of showing you where the agent is placing the gates. But all in all, you can see that, the agent doesn't know much about the system. It doesn't know what to do. Entanglement is steadily, growing up. Now, if you train for about 10K iterations, then all of a sudden it starts realizing that there might be some interesting structure that emerges in the system. In other words, that it can do something in order to prevent entanglement from building up. But clearly it's not doing too well. So if you instead train this until convergence, then it's very clear now what's going on. So the agent figures out how to place bottlenecks, entanglement bottlenecks, in such a way as to partition the system into subsystems. And then, because it plays so rarely, 1 every 20 turns, it basically lets the entangler, to fill in those pyramids, right, to maximally entangle them. However, not letting entanglement to cross, across these barriers. So this is a strategy that, if you had to come up with, you probably could have, but it definitely takes, a non-zero amount of time. And I'm going to show you in a couple of slides why it's actually not so simple to come up with, such a deterministic strategy yourself. But before that, let's just analyze this and see what it tells us and what it means. So once again, the learn strategy is the following. We're going to inhibit entanglement spreading by splitting the system into these pyramid subsystems, and then creating those entanglement bottlenecks. So these are special bonds, which I call entanglement bottlenecks, and then what the agent is doing with this strategy actually is guarding, these bottlenecks. So it doesn't really allow entanglement to spread across them. And by doing this, the system is chopped into small systems, and the steady state takes this form of pyramids. So the question, or what I want to show you now actually, is that this pyramid state is actually an area law state if you scale the system up to the thermodynamic limit. So let's do this counting slowly and carefully. So you can kind of see here, I'm interested in the total entanglement. This is the entanglement across all these bonds. So that's more or less the area that I have here. And as you know, if I have a maximally mixed state, maximally entangled state, that this corresponds to this light gray shaded area, the page curve. And because I have about n of those bonds, then I know that, the area under this pyramid is essentially n squared, okay? So maximally mixed page state goes as n squared. Now, the pyramid state goes like the following. So let's try to estimate its entanglement content. Let's just consider a smaller system first with only 2 pyramids. Now, if I double the system size from n, let's say, to 2n, then I double the number of pyramids. And because entanglement is the area of these pyramids, then what we see is that entanglement also doubles. But, this argument then immediately convinces you that the total entanglement scales linearly with the number of bonds here. And therefore, if you calculate, what's the relative entanglement to the maximally mixed state, then you see that it goes as 1 over the system size. And therefore, this pyramid state is an area law state. As you scale up the system size, this height here shoots up, but those remain more or less the same. Okay, so that's the first thing that we see. Now, another thing you may wonder is, okay, so, we found like this strategy, but is it actually better than the previous ones that we saw, right? Maybe it's not. So the plot here shows a comparison now with all the different curves that we've seen so far. So in green, we have the random agent. In blue, we have the greedy agent. And now the RL agent comes in red. Once again, this is a total entanglement as a function of the bias parameter P to play the game. And there's, the critical point for the random agent, and there is another critical point for the greedy agent. What we see is that the reinforcement learning agent always outperforms all of the others, right? And not only that, but it looks like as you scale up the system size, the total entanglement actually goes down. So this is something that we're going to come to in a second. But before that, let's just play with the agent a little bit more, and let's just see how much better is it, or in which way, in which sense, is it better than the greedy strategy. So I'm going to do the following. I'm going to train, the reinforcement learning agent, and then I'm going to run a trajectory and get into the steady state of the reinforcement learning agent here, which corresponds to this probability. And then I'm going to start, so this is the steady state. I'm going to start from the same steady state, but I'm going to give it to both the RL agent and the greedy agent. And I'm going to show you in a second how both of them are basically, dealing with that state. And again, in the middle, what we see is the entanglement as a function of the, the circuit time. So let me tell you right away, this is going to go relatively quickly as a movie. So this is, on the right-hand side is where interesting thing will happen, where the greedy agent is going to be struggling essentially to keep up the bottlenecks. As you can see, at the moment you lose a bottleneck, it's basically game over, right? So you've created the entropy, and then there's not much you can do about it. You cannot guard it. Whereas what the reinforcement learning agent keeps doing quite successfully is it's trying to basically, not only to keep the bottlenecks, but sometimes, there's a little bit of fluctuations, a little bit of competition. Maybe it can destroy a pyramid. Maybe 2 pyramids will occur there, right? Depending on, how frequently it goes. And this behavior you find because, this agent once again plays so rarely, right? If, you pick up a probability that is, above the critical points for the greedy strategy, then actually we find that the reinforcement learning agent behaves greedily, right? Because it suffices to play the game. There's no need to do anything else. But what's interesting is that there's this very scarce resource regime here, where it actually manages to prevent entanglement from building up. Should speed up a little bit. So now, there's another thing we can do, and I want to now ask the question, well, do these points actually here vanish as we keep increasing the system size? The problem is we cannot really do simulations for larger than 128 qubits so far, or even if we could, it would have been maybe 256 or so. So we need to do some smart counting. And what you see here, once again, is the reinforcement learning strategy for 3 different values of these probabilities. So let's look at the steady state here, and let's try to formulate a steady state conditions for this pyramid state to occur. Now, the steady state condition is that the probability to remove a bit of entanglement has to be the same as the probability to create a bit of entanglement in every given step of the game. So let's see what the probability to remove an entanglement is. Well, so first of all, that's the probability for the disentangler to play, which is P. But then you also have to multiply this by the available configuration space, if you wish, or the available phase space. And the available phase space for the learn strategy is the following. So, okay, this is the number of active bonds divided by the support of the strategy. So what's the support of the strategy? Well, we only place, in this idealized fashion, gates on the bottlenecks. And what's the number of active bonds? Well, in order to disentangle, to remove entanglement, the only place this can happen here is actually those bottlenecks, right? At the same time, this has to be equal to the probability to create entanglement, which is equal to the probability for the entangler to play, 1 minus P, times its own available bond density. And now, here you get to appreciate actually how smart this strategy is. So the available bond density is the number of active bonds. But what are the active bonds? The disentangler can place anywhere on any bond it wants, but it won't do anything on this state unless it places the gate precisely at the bottleneck. And the reason for this is that each subsystem is maximally mixed. And therefore, it can place a Clifford gate there, but this Clifford gate is not going to change entanglement. There's no more space to put more entanglement in the system. Okay, and this is kind of, you see here, how cool of a strategy this is in some sense, because you play so infrequently, right, once every 20 moves, but then you figured out a way how to push your opponent into a corner and constrain its own moves, make them inactive mostly, right, in such a way that you can win the game, right, you can outperform it. All right, but anyhow, this is the steady state condition. Now, you can also estimate the total entanglement versus the number of bottlenecks. Now, the number of bottlenecks is proportional to the number of pyramids you have, and the total entanglement is just the area. So what you find is that, the area of the pyramids divided by the area of the page state essentially goes inversely proportional in the number of bottlenecks. What you can now do is you can solve this equation for the number of bottlenecks, and you can plug this in. And if you do that, you find that the total entanglement, relative to the page state for any probability P scales as the inverse system size, okay? And therefore goes to 0. And so what this means is that even though we cannot simulate larger system sizes, what you find is that the reinforcement learning agent, this learned strategy, essentially completely eliminates the volume law phase and shrinks it to a single point, right? Where essentially it doesn't get to play at all. All right, now I get like 5 more minutes to show you a few more things. At this stage, you might be thinking, oh, but wait a minute, right? Like, these bottlenecks, okay, right? They look cool, but maybe it doesn't take a reinforcement learning agent, to find them, right? So can I actually, do this myself, right? Without any fancy schmancy agents here. So let's come up with the following ad hoc deterministic strategy. So we know roughly the length of our system. We kind of see that these pyramids are equidistant, right? So we basically know where these bottlenecks are going to appear. So let's fix the bottlenecks. Once we fix the bottlenecks, we're going to adopt the following greedy strategy. We're going to remove entanglement one step at a time, starting from the leftmost bottleneck, right? So I go to the leftmost bottleneck, I check, is there entanglement there to be removed? If yes, I place the gate, I'm done. If there is none, then what I can do is I can look at its nearest neighbors. If there is entanglement there to be removed, I remove it. If not, I move to the next bottleneck, and so forth, right? And then the whole thing continues. And now you're going to see, what this strategy essentially does. So it, tries to keep the bottlenecks, but as you see, it's not that efficient in doing this. And in particular, once it loses a bottleneck, like I said before, there's no way of going back, right? It might be able to keep it for a little bit longer, but that's essentially it. And the other thing that you see in this movie is that there are these waves that are kind of coming out here, like these excitations essentially to create the system. But the take-home message from this video is, active feedback control is essential for stochastic dynamics. Of course, you can say, oh, fine, but maybe I shouldn't just look at the neighbors. Maybe I can go to the next nearest neighbors, next nearest neighbors, etc. So the statement here is that, these active feedback control agents, they're actually useful because you don't need to specify the locality, right, of where they act, right? So in some sense, they get to learn how to respond, to perturbations that occur in the stochastic dynamics. And finally, I want to tell you about what happens if you now start asking the question, well, is actually the access to the complete quantum state necessary in order to suppress entanglement here in these games, or can we get away with less information? And like I said before, this is another reason for why we should use reinforcement learning, because it allows us to dial the amount of information. And so what we're going to do is the following. So at each step, as I said before, the agent observes the Clifford state, so the tableau. But what I can now do is I can, with some other probability Q, essentially start removing rows from that tableau. What this corresponds to is dropping some of the stabilizers. And if you actually do the math, you'll find that, a tableau with some of these removed corresponds to a mixed state with a purity, which scales exponentially with this probability. So somehow, the probability of crossing out rows from the Clifford stabilizers from the Clifford tableau essentially corresponds to the entropy of the mixed state, to the purity of the mixed state. Okay, so that's now what we're going to do. And the question is, what happens, with these transitions as we dial Q? So what I'm showing you here is, again, the total entanglement, but this time as a function of the system size, in powers of 2. And the different curves, different colors correspond to different values of this information fraction Q. Okay? And what you see here is that if you have complete information, so that is to say, if Q is equal to 1, then as expected, and we've seen this in our previous argument, the total entanglement basically normalized to the page value goes down with the system size. But what you see here is that, if you have less than perfect information, the total entanglement keeps going down with the system size until a specific critical value of this information fraction is hit, and then beyond that critical value, you no longer can sustain the area law state, and then you revert and you go back to volume law. So what you can do is you can, ask now the question, well, can we draw something like a phase diagram where on one axis we have the probability to play the game, and on the other axis we have this critical information density, and what you end up having is something like this. So x-axis is probability to play the game, y-axis is the critical information density. If you have no information whatsoever and you're playing with a random strategy, then that's this black triangle here. On the other hand, if you have complete information and you're playing with a greedy strategy, then this is this point there. And then the colors correspond to what we believe the learn strategy actually does. So we have 2 data points on the left. These 2 data points are shown here. And of course, the boundary is just schematic. But in particular, what's important here is that there's a sharp transition between an area law and the volume law in the amount of information that you use in order to do active feedback control on these systems. Okay, I think I'm 5 minutes over time, so let me try to wrap it up. So what I've shown you is that access to information can change the critical properties of steady states, even in unitary circuit dynamics. In particular, active feedback control breaks detailed balance and allows us to sustain non-equilibrium steady states. And not only that, but the learn strategies that we've found using reinforcement learning are capable of completely suppressing the volume law phase and leaving only an area law state. And all of this has been done for Clifford circuits. And one of the questions that we still have open up is, what will happen with, if you have a high random circuit? So I can speculate on this, but we haven't done these simulations yet. Now, second, active feedback control seems to be absolutely essential for stochastic dynamics. In particular, if you just try to use deterministic ad hoc strategies, then most likely, if, unless you allow them to be non-locally supported, right, like they are going to fail. But not only that, reinforcement learning seems to be the right tool to do this because you can, first of all, dial the amount of information, and second, it's naturally suited for this kind of interactive feedback control that you want to do in this. And finally, complete information about the state of the quantum system is actually not necessary. What we find is a critical information threshold in order to stabilize area law steady states. And some things that we've been discussing, with Richard is, whether we can use this now, this little daemon, to protect information in an initial state, whether we can do this in higher dimensional systems where you would probably see the nature of the pyramids. But, if I have to, summarize everything with just one sentence, it would be, don't be greedy, or whatever you do is very highly likely to be reduced to a pile of sand in the longer run. On the other hand, if you try to go in a smart strategy with a smart way, then what you do is most likely going to survive, the time, at least temporarily. So thanks a lot for the attention.
Questions? Yeah, thanks, Marin. Very nice. But there was a point which I may have misunderstood. So you kept referring to this as a unitary circuit game without any measurements, but aren't you measuring it to know the entanglement?
Yeah, so this is a stabilizer circuit. So for as long as you can keep track of the state, you can measure all the stabilizers without destroying the state.
I see.
So
but it is a measurement feedback game. It's a unitary plus measurement and a feedback. So it is within the
technically
realm.
there is no measurement.
But you have to know what the stabilizers are.
So this is, I guess, maybe where your intuition is coming from is basically the same thing, why Maxwell's daemon, it looks like it can reduce the entropy without really doing any work on the system. So that's because, in order to, restore second law, you have to consider the daemon and the system. So here it's similar. If you consider, the agent and the system, then the amount of entropy / information, of course, is conserved, right? And then you can say you have like measurements, etc. But if you consider the agent as external to the system, you can still, by looking only at the system, end up having just purely unitary dynamics, right? But that unitary dynamics, of course, is going to go into steady states, which are otherwise not going to be possible. So implicitly, there are no explicit measurements, but implicitly there's information flow. And it's this information flow essentially that allows us to stabilize steady states.
I see, thanks. And then one more comment. So what's the relationship to this entanglement heating and cooling game by Alyosha Hama from 2014? Are you
I know what you're talking about. So they consider high random.
No, they also consider Cliffords as well.
Okay, maybe they also consider Cliffords, yeah. But what's important here is that, we're not doing any cooling, right? So, and this we see, and this is actually the difference actually to a proper Maxwell demon. So a proper Maxwell demon will start in a high temperature state and then, get rid of entropy here.
No,
what we're doing is
similar, actually. Like they were looking at entanglement across bonds and applying a disentangler.
Okay, I know the paper, but I guess I need to look this up again.
I see, okay.
Yeah. I was under the impression that what they're doing is they're trying to remove entanglement. And they were showing that it doesn't work. Here, I'm not removing entanglement. I'm preventing entanglement from building up. And I think that's the easier task.
Right, okay, thank you.
Thanks, very interesting. I'm slightly concerned about the way you call it area law entanglement, because I have a question like, what's the parameter that determines the number of these little pyramids in the
number of bottlenecks?
In the steady state, for example, number of bottlenecks.
So that's set by the probability so how frequently you play and the system size.
And you claim that this is proportional to n, the number of bottlenecks?
Yeah.
I see.
So basically what we see, and it was more or less like this argument is that if you increase, if you double the system size, you'll double the number of pyramids, the heights are going to remain the same.
I see. And
that's also what we see in the numerics. And because of that, the area remains linear in the number of bonds, but then of course you have to compare it to something, and you compare it to the page state, and the page state, is quadratic in the system size, because that's the area of the full pyramid.
Also, this is strangely reminiscent of a model of KPC service growth.
That's absolutely true, and I didn't mention this. I think if you only go to the entangler plane, so basically you go to the point where p is equal to 1, then this is, I think, like this old story of, surface growth and unitary circuit games, surface growth and where you can map it to a KPZ problem and extract the critical exponents. From what I know, the critical exponents can be extracted, for instance, for the green curves. They can probably also be extracted for the blue curves, but I don't know of a specific universality class that they are assigned to.
Right.
So the problem changes there. And for the red curves, I don't think it's even feasible to do this with this data.
Thanks.
All right. So it's really impressive that the agent figured out this strategy that take advantage of the subadditivity of entanglement, that the slope cannot exceed 1. Therefore, it's essentially frozen, and so you can
precisely. So it learned how to deal with the constraints there.
Right. So I'm wondering if you choose other geometry, for example, 2-dimension, would the agent also figure out other properties of entanglement, such as strong subadditivity, that uses that, build that into this game strategy?
Great question. Short answer is I don't know, but we are currently looking into 2D.
Okay.
Yeah.
And also a related question to one way. So here it looks like you are trying to prevent the entanglement from growing, and so. But I guess the more interesting question is that if entanglement already is volume law, is there some heuristic that you can get to decrease the entanglement?
Yeah, we looked into these, and it wasn't possible to pick up enough information for the agent to learn. Okay. So it's, it goes one way, right? It goes the easy way. It goes the physical way in some sense.
Okay.
Yeah, that's why I was trying to be careful, with the formulation. So we're trying to prevent entanglement from building up. We're not trying to disentangle states.
I see.
Yeah.
Thank you.
Yeah, thanks for the nice talk. So sometimes in games, there can be situations where using a probabilistic mixture of a few different deterministic strategies performs better than like one strategy alone, because it's just like a little more robust. And I was just wondering if you think, that ingredient is enough to like already stabilize the phase, or if you really need a lot of information out of it.
Short answer again, I can only speculate, right? Mm-hmm. So my intuition is that the reason why a probabilistic mixture of deterministic strategies may not work here is because the advantage of this active agent is that it reacts, right? So it responds. If you have a strategy where you flip a coin, right, every time, it won't be able to respond. And the problem with this, and this was essentially what this movie here, what this movie is showing is that at the moment you lose the bottleneck, right, then it's basically game over, right? There's, it's difficult basically to cool, to extract, right? That goes against the second law. It's a one-way process. So this is why, this is why we're currently, of the opinion that, this active component is actually essential for this. But again, the honest answer is we haven't tried, and it could be that we find something different.
Okay, thank you.
So I'm wondering to what extent the discreteness of the Clifford group is fundamental to the story, or if some of this would be robust to taking a continuous gate set.
So that's a good question. Once again, short answer, we have to see, right? But we are thinking about this. So how to do this with high random gates. Now, there are a few things that one has to mention if you want to do this with high random gates. So let me move to something where we have pyramids. Yeah. And what, okay, so like I said, like a few things we have to mention. So first of all, you could imagine that you could be able to simulate big system sizes, like to see that if you have some sort of matrix product states. Now, this actually happens to be important because if you go to system sizes of about 16 qubits or so, then you don't see any pyramids. The entire time, like the agent is more or less converging to the greedy strategy. And so in order to see, a collective phenomenon, you need to go to big system sizes. So now what you can imagine doing, and this is what we want in the end to do, is we want to go to, a system with high random gates where we more or less know where to place these bottlenecks. And then we give our agent a sufficient, the probability to play sufficiently quickly. Now, my intuitive understanding is such that if you know how to define in a good way a disentangling gate for high random states, and there are examples of this, then for as long as the disentangler plays often enough and you start from a product state, it's going to win, right? So then there's going to be some critical probability, right? And then the question is, can you push this critical probability all the way down to 0 or not? And intuition again is that this won't be possible, but again, one has to see. And whether we're going to be able to simulate this is, I think, the big question, right?
Yeah, I was going to suggest to the end thinking of match gates, right? They're simulable like Clifford's, but they are continuous.
Exactly. So yeah, I think in the group of Frank, they already did something like this with match gates, but not with reinforcement learning. They were just doing the random agent strategy, essentially.
Okay, thanks.
Yeah.
Thanks for the great talk. I was wondering if you could maybe expand a little bit on Wenwei's question about how measurements really come into this, particularly in like a quantum manner.
Yeah.
This being all Clifford gates, I can kind of understand how you might have, this kind of effectively classical dynamics. You have a probability for something to move one way or another, or you apply this gate or not.
Yeah.
But if you have, say, like hard random gates, then the measurements can be non-commutative. They
Absolutely.
can change the system. So how do you kind of move the daemon out of the system in that case? How do you make this kind of, I don't know, how do you characterize this as a quantum, not a classical daemon, same way?
So the short answer is that, this way of feeding, the full state, or giving it to the daemon, right, for high random states is just not going to go. It's also not the experimentally, meaningful thing to do, because what you would want to do is you would want to, take a snapshot and feed only the snapshot. I do think that, it will be very interesting, and, more or less this is what we were trying to mimic when we said that we want to, start crossing out, like some of these stabilizers, because that was just easier for us to do. But before even one goes to high random state, what one can do is one can extend the Clifford tableau with the measurements, and then one can actually simulate the whole thing with measurements and see whether measurements behave differently than this. And we were discussing this last week also with Richard, and there, like one setup that's kind of interesting is that if you have, entanglement between two qubits that are far away, and you happen to cut that bond, right? Cut the entanglement bond, what I mean, right? Then you basically disentangle them. But if you're only, limited to local Clifford unitaries, then you have to apply a whole bunch of those. So it could be that the measurements actually makes the problem simpler. And this was sort of our original motivation for why we wanted to go fully unitary here, right? And the other thing is, I don't think I can sell this to an experimentalist because, they want to show quantum advantage, and this is not really quantum advantage, but I think you can learn a lot about what might actually be interesting to try in a high random setting.
Thank you.
I have a very basic question. Can you clarify the notion of detail balance for random unitary circuits? Because we don't usually think of that as a detail balance process.
Exactly. So once again, it's fairly straightforward. Here. Yeah, so it's fairly straightforward. So you have a stochastic dynamics, right? Think about this dynamics as dynamics that defines a Markov chain on your stabilizer state. So the set of stabilizer states is a discrete set, right? So it's literally like a discrete Markov chain. And then what you do is, with certain probability, you transition between states. And now what we know is that, as we are playing that entangling game, right, in the longer run, the entanglement gets into some steady state, right? And so there's some mixing time for this Markov chain. You wait until you go into the steady state, and then in that steady state, you ask the question, does the steady state probability distribution, obey detail balance or not? In other words, is it an equilibrium? So in other words, can does every move lead to a reverse, has the same probability as the inverse move, right, or not? So that's essentially how you do that. Thanks.
Any more questions? Well, if not, let's thank the speaker again for a very fun talk. That's the end of our conference, but let's also thank the organizers for putting together this wonderful conference.
Yeah, thanks to all the speakers for the great talks, and thanks to the audience for the intellectually stimulating questions. I hope you guys had a great time here, fun and productive time, and wish you guys a safe trip back to wherever you came from. Thank you.